Welcome to Investigation 6. This is a good one. This one is chemical reactions, what we've all been waiting for, right? In this first part of the unit, we're going to look at modeling chemical reactions, different ways to represent a chemical reaction. Now, obviously, in a chemical reaction, you start with some kind of reactants. The reactants are the initial substances that you start with, and you form products. The products are what you end with. So we're always going to have reactants and products. Let's see if I can highlight those. Reactants are what I start with. Products are what I end with. Now, we might have two reactants and two products, one reactant and one product. We can have four reactants that make one product. The amount of reactants and products does not matter. We can have lots of little things that join to make one big particle. One big particle can break down into little things. It's going to be great. There's endless possibilities. Now, the key with a chemical reaction is that you're forming something new. So I'm taking the initial reactant and I am chemically changing them so that it is a new product with new properties. And so an example might be like iron reacting with oxygen to produce iron oxide, commonly known as rust. So we know iron is a metal and it reacts with just oxygen in the air and eventually forms kind of that, like rusty colored, kind of brownish red colored solid, which is iron 3 oxide. It has totally different properties from the initial iron metal and oxygen gas, totally new properties. That's the key to a chemical change or a chemical reaction. Now here they're just showing us that there's different ways that we can represent a chemical reaction, the reactants and the products. Sometimes we write it as a word equation. So you might have like a description of the reaction. Iron and oxygen react to produce iron 3 oxide. Well, then we might kind of write that as words. So my reactants are the iron plus the oxygen. They're forming my product, my iron 3 oxide. And so that arrow shows me the conversion from the reactant to the final products. They give us another example of writing a word equation with I'm baking bread, where the reactants are everything that you're starting with, all your ingredients. Flour, eggs, milk, salt, baking powder, oil. They all react together to form one product, my bread. So you might see it written as words, or we could represent an equation as symbols, or sometimes we try to model the reactants and the products. Like, what would these things look like on a particle level? So here they're representing something called a skeleton equation. A skeleton equation is just a chemical reaction that shows the reactants and the products, but not necessarily the right amount. It's pretty bare bones, get it? Skeleton reaction. And so we could write a skeleton reaction with words. So maybe it's something like hydrogen reacts with oxygen to form water. And so the hydrogen plus oxygen are my reactants. I might write it as words. To form water, well then water would be my product. And the arrow sends me from the reactants to the products. You might also write it then with symbols or with particle models. So now they might tell me that hydrogen and oxygen are diatomic gases, which maybe we should just kind of make note of that. Diatomic is an element that exists as two atoms. Two atoms joined together. On your periodic table, if you want to, you can mark these in. You've got that periodic table in the back of your book. The diatomic elements are hydrogen, and then over on the other side of the periodic table, it would be nitrogen, oxygen, and all of the halogens, fluorine, chlorine, bromine, iodine, and astatine. Although we don't really use astatine very often. But these are the diatomic elements. Hydrogen, and then nitrogen, oxygen, all down the halogens. I kind of remember it because 1, 2, 3, 4, 5, 6, 7 of them make the number 7. Like nitrogen, oxygen, fluorine, all down the halogens. 7 of them kind of make the number 7. And then also little baby hydrogen. They're elements that just come in nature paired as 2 atoms bonded together. So elemental hydrogen really is H2. Elemental oxygen is O2. And they react to form water, H2O. So again, we might write it as symbols, or we might kind of model it with particles. That hydrogen is a pretty small atom, so H2 would be like 2 little hydrogen circles bonded together. O2 is 2 oxygen atoms bonded together. Oxygen's a small atom, but it's still a little bigger than hydrogen. And then H2O could be represented with 1 red oxygen and 2 small white atoms of hydrogen. Now the other thing that we sometimes like to add to our equations are called phase symbols, where we write these little symbols behind the particles to show like what phase they are. It just gives a little bit more information to somebody that's looking at a chemical equation. So we might write like hydrogen gas reacts with oxygen gas to produce water, which is normally a liquid. I mean, it could be solid or gas, but under normal conditions, water is probably produced as a liquid. Question 3 then says to write the skeleton equation for the reaction of iron and diatomic oxygen gas to form iron 3 oxide, which is the rust. So if I wanted to write this as like a skeleton equation, maybe I would write it just like that. Iron is just Fe plus diatomic oxygen gas. That just means that the oxygen gas is going to be paired. Okay, so these are my 2 reactants, iron and oxygen gas, to form, that means my arrow, and then iron 3 oxide. And how generous. They're even giving me the formula. That doesn't always happen. Sometimes we might have to say, well, iron is +3, oxygen is -2. So yeah, I can still write formulas. So maybe this would be like my skeleton equation or my kind of symbol equation. We can also kind of sketch a model of what this might look like on a particle level, where maybe I would have like atoms of iron. Maybe I'll just do the iron as a blue atom. And then the oxygen, maybe I'll do that as like a red atom. So oxygen's a little smaller, and there'd be 2 of them joined together. Then they react to form this Fe2O3. Now, you don't have to draw this to the proper like crystalline structure. So as long as you do something that maybe had 1, 2 iron atoms, and then 3, 1, 2, 3 smaller oxygen atoms. We get it. Now in reality, it's like a crystal of alternating iron and oxygen ions. But here we're just trying to represent the particles present. And this is all we would need for either a symbol equation or one of these particle models. Now you might be itching a little bit because you've heard something about like equations needing to be balanced, maybe, where I'm supposed to have like the same number of iron and oxygen atoms on both sides. And right now I don't have that. I only have 1 iron on the reactant side and 2 iron on the product side. For now, that's okay. We're just trying to get like a general skeleton equation. What are the reactants? What are the products? And then eventually we'll tackle the beast of balancing the equation. Finally, here's a nice chart that shows a lot of the symbols that you could see in a chemical equation. So obviously we could see the plus. The plus shows me all the reactants, what's reacting together. We could again have 2 reactants. We could have 3, 4, 5, 6 reactants. The arrow shows me what is formed as a product. It stands for like yields or produces. So if I have a description of a reaction that's like iron reacts with oxygen, I could say iron plus oxygen. And then you might say it yields iron 3 oxide, or to produce iron 3 oxide. When you see that arrow, it's always pointing toward the products. Now, sometimes you could get a reversible reaction, where then you'll have like a double-sided arrow. Not something that we'll focus on or that we'll see a whole lot in a first-year course, but that is something that we would talk about in a second-year course. What happens if you have a reversible reaction where eventually the products might turn back into the reactants? Pretty crazy. For sure, we will see these next couple symbols, solid, liquid, gas. They just give us a little more information on what things would look like if I were running this reaction in a lab. And we'll also use the symbol AQ quite a bit. AQ stands for aqueous. It means that something is dissolved in water. And so, for example, we could have something like NaCl solid. And if I saw that as part of a chemical equation, I would assume that somebody just went and got some solid salt. And they're going to mix that solid salt with something else. If you see NaCl with a little AQ, aqueous, now that means that it's a salt solution, that somebody dissolved the salt in water. Oh, interesting. Now, there's one thing that does kind of come up a little bit, and it's the difference between aqueous and liquid. Where they'll say like, well, what's the difference? I mean, this would be a sodium chloride solution. This is like a salt solution. It's salt that's been dissolved in water, so it's going to look like a liquid. And so then they're like, well, why don't you just use the L? The L liquid is only for things that naturally occur as a liquid. So occur as liquid in nature. Well, sodium chloride is naturally a solid. And if I dissolve it in water, it looks like a liquid, but it's because it's a solution now. And so then we use the symbol AQ. The L liquid is only for things that naturally occur as a liquid. So obviously, like we use it a lot with water, or maybe some alcohols naturally exist as liquids. Or it could be like acetone is naturally a liquid. Like rubbing alcohol, things like hydrogen peroxide is naturally a liquid. It's actually a symbol that we probably don't use a whole lot. But the aqueous is very, very common. It means that it was probably originally a solid, but I've dissolved it in water. You might see symbols that indicate that your reactants are being heated or that heat is being added. So you could see an arrow with heat above the arrow, or maybe a little triangle. And that just means that your reactants are being heated to produce whatever is on the product side. You also might see like a symbol above the arrow. The symbol represents the use of a catalyst. And a catalyst is really just something that speeds up your reaction. And so it might be that my reactants only react with the assistance of a platinum catalyst. It's something that's speeding up the reaction. But it's not something that is part of the equation. So for example, we will run this reaction in class. The decomposition of hydrogen peroxide. H2O2 is hydrogen peroxide, and it decomposes to form water and oxygen. That does just happen in nature. That's why, like, your hydrogen peroxide in the medicine cabinet is stored in a brown bottle, just because, I mean, ultraviolet light naturally that's around us is enough energy to kind of split apart the H2O2 molecule into water and oxygen. Well, the darker colored bottle just kind of blocks out some of that UV light. Well, I mean, in the bottle, that decomposition happens very slowly. But in the lab, I might want it to happen faster. So you can use a catalyst. And one common catalyst is potassium iodide. The potassium iodide catalyst just provides a little lower energy. We say it's lower activation energy, which is kind of the answer to question 4. Lower activation energy, which is energy. Whoopsies, I should put energy in there. Activation energy, which is energy needed to start a reaction. That's kind of how a catalyst works. Number 4 was asking you to do some research on why manganese 4 oxide could also be used as a catalyst. It could be manganese oxide, it could be this potassium iodide. There's lots of different catalysts out there. All they do is provide a little lower activation energy. And activation energy is just the energy you need to get a reaction started. So if I use a catalyst, I don't have to add as much energy to get the reaction started, so it goes faster. The same reaction will happen without the catalyst. It's just that it's going to be slower. And so the catalyst is written above the arrow because it's really not a reactant and it's not a product. The catalyst isn't changing in any way. It's just affecting the energy level of the reaction. It's adding a little boost of energy so that I can get the reaction started a little bit quicker. But it's not changed in any way. So it's not written as a reactant or a product.